in this imprecise interrupt handling technique, you need to save all the information about all these instructions. I mean, for this case, you need to save only the program counter, right? Just save the program counter. For this one, you need to save all the information related to these instructions. And you need to save at what phase that instruction is being executed. That's a very complicated information. That's why imprecise interrupt handling is not something easy. You need to, the CPU has to be very, very complicated. The operating system, the interrupt handling routines, they need to be very, very complicated to handle this kind of situation. You need to, when you go back executing your instructions, you need to restore all of your execution stages of your instructions exactly before the interrupt has happened. This one is simpler. This one is simpler, but this is less efficient. Why? Because it waits until all the instructions clears the pipeline. Okay? It waits until all the instructions clears the pipeline. This one doesn't wait, but this one is slow in terms of writing all that information, saving all that information to the memory. So when we talk about some kind of a technique in this operating system class, we only talk about beginnings of the problems that they are facing in writing the real code. Operating systems are very, very complicated software, right? They are very, very complicated. Writing operating systems are not easy. And we are only talking about the main concepts. We are not going into the very details of the operating systems. I mean, handling this kind of imprecise interrupt by itself is a very complicated project. Okay, maybe a number of very good computer engineers or computer scientists should work on it to implement it on a new system. Very complicated, but somebody has to do it. Yes.
Isn't it doing hardware? Why are we doing OS? Because it's part of CPU, so CPU should handle the interrupts.
Yes. Well, the hardware says that, okay, from the hardware, when the interrupt happens, the hardware says that, okay, there is an interrupt happened and I saved the PC program counter. That's all you get from the hardware. All the rest of the stuff needs to be saved by the operating system, because doing that kind of a complicated software stuff on hardware is very expensive. They don't want to do it. When you handle that kind of stuff on the hardware, your hardware becomes larger and larger. Instead of spending that kind of resource on the hardware, they say that the operating system is going to handle this, and your hardware can become smaller and faster, and it doesn't produce that much heat. I mean, it is possible to handle everything in the hardware, that's true, but that makes the hardware more complicated, less efficient. Okay? And sometimes different operating systems handle this interrupt differently. Okay? Windows and Linux, they can run on the same platform. Their interrupt handling routines are different. It depends on your environment. Sometimes you want to handle that way, sometimes you want to handle it that way. Okay. So if it is handled on the hardware, then you have no choice but to use it. Sometimes you don't want to do it. Solutions in the software is always more flexible. Okay. May not be most efficient, but it's always more flexible. Even on the same system, sometimes the system uses precise interrupt for some cases, sometimes it uses imprecise interrupt for some cases. With the hardware, you cannot make these kind of decisions. There was another question.
Ben diyecektim hocam, bir insan için %10 ihtimali çalışması ne anlamına geliyor? Zaten seçtik orada.
That doesn't mean 10% probability. That means that it is 10% completed. 10% completed. Suppose you have a scalar structure like this. Okay. When you are at this phase of the instruction execution, this instruction is 2/3 completed. This is all completed. This is 1/3 completed. Okay. So this is, let's say this one is 100% completed. This one is 2/3 completed. This is 1/3 completed. Okay. It's not the probability. It is how much of the instruction is completed. And this is a very simple scalar architecture. Some scalar architectures have 10 phases. Okay. So it is possible that one of the instructions is only 10% completed.
interrupt bittiğimizde devam
Yes, when the interrupt is finished, you need to go back and continue from where you left off, but you need to save all that data from all of your instructions. Sometimes you need to save, saving the program counter is not enough, because each instruction is performing something, they are modifying the registers, right? So you need to save all of those registers for each instruction separately. Okay, and you need to save the state too, at what state it is in. So that makes it more complicated for the imprecise interrupt handling. Okay, for the precise interrupt, PC is stated at no place. All instructions before that point in PC are fully executed. No instruction beyond that pointed to by PC has been executed. An execution stage of instruction pointed by PC is known. Okay, so in a scalar, in a pipeline system, if you executed an instruction in a halfway, then you need to undo whatever it did on the system. Okay, sometimes you may need to undo some of the operations of some of the instructions. Undoing some of the stuff is not easy, but it is possible. They already implemented it. Partially complete instruction needs to be undone. Otherwise, this is not called precise. It would be imprecise. Okay. I think I am out of time. I think I will stop here. Next time we will finish this imprecise interrupt and we will start talking about the software side of the IoT.
Sağ olun.